go. Hello, good morning. Hello, YouTube, and hello from my faint attempt to try to make this presentation slightly visually more interesting. Look, I'm close to that. All right, or maybe to blow out your speakers, depending on how well the mic placement worked there. Anyway, so so the reading for today is 16.7, the main theorem of Galois theory, and for Wednesday we'll actually start. After that, for the rest of the semester, we'll be applying Galois theory, and this will be cool. So we'll actually solve. God forbid, we're actually going to complete a project started in college algebra. We're going to starting on Wednesday, we're going to solve cubic equations, and then after that, quartic equations. I mean, let's see how far this goes. And so on up until perhaps the quintic, and then maybe we'll pull back and do something else. Anyway, right. So problem set 10. So there is a problem set 10. You may have seen problems. I've assigned problem sets through the end of the semester. Problem set 10 is due on Monday, April 27th. But as you know, all deadlines are elastic. And a last minute announcement here. At least tentatively, that we'll have a take-home exam number 3 due Monday, May 4th, and then we'll have a take-home final. All right, and today's DJ was Ravi. Thanks. So now everybody's done it. Robert, Robert, you're sort of our guest here, but if you want to pick us, actually, I'll email you later. See if you want to pick a song for Wednesday. This is our little ritual now, is that we play a song before class, because I don't know, because I found the audio screen share thing interesting on Zoom. Oh well, excuse me. Anyway, so are there any questions? Oh, thanks, Robert. Okay, so Robert will provide a song for Wednesday. Are there any questions before we go ahead and get back going on Galois theory? See what this is? Totally water. I mean, it is. I'm basically a boring person, but you gotta make that joke, right? So, no questions? Okay. So morning all, and let's get going. Oh, Robert, you had a question? Robert, did you have a question? You can unmute. Oh, maybe I have to unmute you. No, Robert, your mic is actually open. So
okay, no, I just opened it now. Can you give me permission? Thank you, Dr. Sue. And so here's a question. It's easier for me to say it than type it in real quick. And you could take it at the end if we have time or now. So when I'm reading through Galois, and you helped me to understand one of the other theorems, that it was all the roots. For the roots of polynomial, we know that we can have distinct roots, or we can have roots of that are repeated with some multiplicity. So sometimes when I read the theorems, if they say D roots, then I know they're distinct. If we know we have one root and we're referring to an orbit, the orbit set will be distinct elements. So I know that implies that there's distinct. If we have a splitting field for a polynomial, then when I read the definition, it looks like to me that the roots must, of course, be distinct. So in theorem 16.66, before the main theorem, it says that it splits completely, so its roots are, beta 1 to beta r, so they're distinct. So I guess what I'm trying to ask by all that is, when I read the theorem, sometimes I wonder whether the roots are distinct or not.
Okay, so here you have to be careful about this. So Robert asked, when do we have repeated? When do polynomials that we're dealing with have repeated roots? And the answer is because everything in chapter 16 is all in characteristic 0. So the first thing, here's answer number 1. Characteristic 0, all irreducible polynomials never have repeated roots. Right. So yeah. So that was, you know, I think I didn't personally emphasize this too much. Actually, Artin is pretty careful about this at the beginning of chapter 16. But at the beginning of chapter 16, there's some assumption that says, well, we assume all fields have characteristic 0. And I think the main reason for that is because you can then assume that irreducible polynomials must. Well, I mean, there's sort of a there's actually a sort of an echo of this in another result, but basically the main assumption is that irreducible polynomials will never have repeated roots. That will sort of address, I think, most of the times when there's a question of repeated roots. Robert, does that make sense? Okay, yeah. So Robert says thank you. Let me give one other answer though. When a polynomial is not repeated, is not irreducible, is reducible. Of course, we can have repeated roots. Well, I mean, just, you know, take your favorite polynomial and square it, whatever, you know, x minus 2 squared. Look, there's a polynomial with repeated roots. I should put a 3 so it's not repeat numbers. Anyway, so, you know, so for just silly reasons like that, you can have repeated roots, or actually for any g of x squared. So, you know, just for silly reasons, you can have repeated roots for a general polynomial. But I think in any time when we actually need to look at all, so when we talk about all of the roots of some polynomial f of x, go back and check to see that f of x is irreducible. And I think almost all the case, either it will be, or the repeated roots won't matter. Or I suppose there's some sort of mistake, and then you have to worry like really hard. But I think that that should cover it. Okay. Any other questions before we do our recap? Okay. Let's get going. All right. So as always, we like to start. Oh, look! I can finally do this joke for real. You know, we always like to start by summarizing Galois theory in a nutshell. Let's see. Oh, help! I'm in a nutshell. Okay, so sorry if you've seen Austin Powers. That's a joke from Austin Powers. Anyway, so Galois theory in a nutshell. So suppose K is an extension of F that is a splitting field with some irreducible, and the irreducible here corresponds to the transitive. So this irreducible here, I highlight stuff. So this irreducible here corresponds to exactly this word transitive over here, as we'll see. Anyway, so the point is that Galois theory relates the field theoretic properties of K as an extension of F, such as the degree of K as an extension of F, and group theoretic properties of the Galois group G of K over F, which we just usually abbreviate as G, and that which is remember the group of all automorphisms of the field K that fix the base field F. And we know from before that G permutes the roots alpha 1 through alpha n of little f, and is isomorphic to a transitive subgroup of Sn. And did I mention that the transitivity over here, which we'll really start to look at right now, corresponds to the irreducibility back there. And actually, we will look at an example later today where F is not irreducible, in which case this is still true except without the word transitive. All right, so the main theorem, which we're finally getting to today, whew, yay! This is like the highlight of the semester in some ways, but yeah, it's good stuff. So the main theorem says that there's a bijective inclusion reversing correspondence between 8 subgroups H of G, and oops, oh, this is going to bother me to no end that that this is, I use a different symbol here No. There we go. Between subgroups H of G and intermediate fields L between K and F, but not necessarily strictly between K and F, sending H to its fixed field, K, which is denoted K to the H, and L to the Galois group of K over L. The L automorphisms, the automorphisms of the K that fix not just F, but L, which, as we'll see later today, is a subgroup of G. And then sort of between now and the end of the semester, we will look at the signature problem of Galois theory, which is trying to solve the problem of when alpha 1 through alpha n, the roots, the roots of f, there's the roots of f. And the question is, when can we write the roots of f, alpha 1 through alpha n, as a function of the coefficients of f, an expression that uses only kth roots, like square roots, cube roots, fourth roots of k, of the coefficients of f. If we can do that, then f is solvable by radicals, and as you may remember, if you've seen Galois theory before, you may have heard it on the streets. The kids may be trading some rumors about this. You may have heard that that in general the quintic is not solvable by radicals, and sort of polynomials degree 5 and up, they're not in general solvable by radicals, though some of them are. Which is a really interesting thing that comes out of Galois theory. You actually find you can find like a quintic formula more or less that works some of the time, but not all the time. Anyway, so the point is that that in general, polynomials degree 5 and up do not have some sort of formula, some sort of which means basically you can't factor anything of degree 5 and up. So yes, that's right. College algebra is a lie. Yeah, well, it's a good lie. It's an occasionally useful lie, but it's kind of a lie that you can't really factor, or rather there's no better formula for factoring a polynomial degree 5 and up other than the product of x minus the roots of f. That's as good as it gets, actually. Okay, so any questions about that so far? So there's our summary. So we all good with that so far? Yes, this is the new visual interest that we have in the YouTube video, is me drinking water at regular intervals. Okay, so let's zoom back in and move on. All right. Oh yeah, this is where we left off. So we were proving the characterizations of Galois extensions, which says more or less. Let me sort of zoom in on the theorem first before I review the lemma that we will need to prove it. So the theorem, I said, oh no, that was something else. The theorem, there we go, says that K over F is Galois if and only if the fixed no surprise elements in the fixed field of G if and only if K is a splitting field. Yeah, so Galois extensions are the same thing. Splitting fields are the same thing as field extensions, where there's no surprise. Where if you look at all the elements fixed by every symmetry of K over F, then there's nothing extra. There's nothing besides F. And I think what we got to last time is that we showed that 1 and 2 are equivalent by applying the fixed field theorem to the intermediate field, which is the fixed field of G. The fixed field of G, sorry. Okay, so so Galois is the same. I think usually, most often we use that Galois extension is the same thing as a splitting field, but this is occasionally useful as well. All right, so are there any questions about the statement of that theorem? Now you can see what I'm doing while I'm waiting for 10 seconds. I'm actually, there's a clock in this room where I move my stuff, right? My new setup here. I'm listening to the second hand go tick, tick, tick. You might even be able to hear it faintly on the video. I don't know. Okay, so that's what we got. Last time we showed that 1 and 2 are equivalent, and by the fixed field theorem. I mean, basically the equivalence of 1 and 2 is the fixed field theorem. And so now we're going to use now we're going to Now we're going to use this lemma. So suppose K is an extension of F by a single element gamma 1. So K is F of gamma 1, and F is the irreducible polynomial for gamma 1 over F. So let gamma 1 through gamma R be the roots of F that are in K. Right. So I guess this, going back to Robert's question earlier, we are assuming that F is irreducible. So there's no question about repeated roots. So let gamma 1 through gamma R be all of the roots of F or in K. There might be, you might imagine that there are other roots somewhere else, possibly. So for each of those roots, there exists a unique element, exactly one element of the Galois group of K over F that sends gamma 1 to gamma I, and which means that which implies that the Galois group of K over F is actually equal to the number of roots, exactly the number of roots of that irreducible polynomial that are contained in K. Let's see, right. So yeah, now we want to prove that 1 is equivalent to 3. So let n be the degree of K over F, just to abbreviate things. So let's see, so that means, oh yeah, so first of all, so because K, the reason that we're able to assume that K is equal to some F of gamma over 1 is that we choose a primitive element. I probably should have left some space down below to do this, or the extension of K over F. So remember, another consequence of helpful consequence of characteristic 0 is that we were always able to, any finite extension is primitive, and so we can choose that primitive element. It's a helpful sort of tool in our proofs to start off with that primitive element, which means that the degree of that primitive element, well, the degree of the primitive element is equal to the degree of that extension, which is n. And so, right. So let f of x be the irreducible polynomial of gamma 1, which means that the degree of f is n. And so what happens now is that now we just have a sequence of if and only if statements. We see that so we want to show that K over F is Galois if and only if K is a splitting. I guess let's start on 3. So 3, K is a splitting field over F if and only if all of the roots, all n roots of F are actually in K. Right. Well, I guess because on the one hand, if all the roots of F are in K, well, then K is a splitting field of the polynomial little f. On the other hand, if K is a splitting field, then an irreducible polynomial which has one root in K has to have all of them in K. So that's that. So K is a splitting field over F exactly when. Okay, you know what? I know that I'll come back to that point in a minute. But okay, but the overview logic is that K is a splitting field over F exactly when all the roots of F are in K, which because the order of G of K over F is equal to the number of roots the number of roots that are in K. That's true if and only if the order of G is n, which by definition, well, that's which by definition happens when K over F is Galois. Well, I can just say 1. Okay, and I realize as I say that, there's a subtlety that I kind of glossed over here quickly. So let me, but I'll go back to it in a second. Subtlety. There we go. All right, you can. Oh, great! This is the visual interest now of this video. Now you can watch me peer the screen and try to write with my finger. Okay. So there is a subtlety in this 3 happens if that K is a splitting field if and only if all the roots of F are in K. Actually, let me erase that. Okay, so but before I get into the details of this subtlety, are there any questions about the subtlety of the green equivalence? Are there any questions about the overall logic of 1 happens if and only if 3 happens? Should I go ahead and explain the green arrow, the green double arrow? Say yes. So I fear that the green arrow is something that I could sort of get away with. I say, well, of course, it's green if and only if splitting field. But let me. So let me. Oops. There we go. So let me talk about what is the subtlety. Oops. Here I think I want to type subtlety of that looks weird as I type it. I think it's spelled correctly, of the green arrow, which is if all of the roots of F are in K, then K contains splitting field F, certainly, because it has all the roots of F, and is generated by F and one of those roots. So K equals the splitting field of F. Oops, sorry, this is splitting field of little f. All right, so if all the roots of little f are in K, then I think it's a little more clear that K is a splitting field of little f. The converse is maybe not quite as clear because if K, it takes a little bit more work. So if K is a splitting field, but not necessarily of F by assumption, of something, splitting field theorem, which we saw a while back, implies that if K contains one root of an irreducible, it contains all of them. So, since by construction, K contains one root of little f, it contains all of the roots of little f. I think in Artin this is done by referring to some previous result, but I guess I'm sort of reviewing that previous result. That we actually kind of subtly use, make a subtle use of the splitting field theorem. I'm so unsure of the subtle part. I think that's one of these things. If you spell a word often, like enough times, it starts to look weird. And now I've made the word subtle look weird. Well. Anyway, so that's the bit with the green arrow. Anyway, so going back to the 30,000 foot view, is everybody good with? Let me see if I can get this. Oops. I want a whole page. All right, is everybody good with the overall proof of the characterization of Galois is the same, basically Galois if and only if splitting field. So we're good with that. Should we move on or ask a question? Okay. Yeah, there's a lot going on here. All right, so let's zoom back in. Oh yeah. So right. So now we want to do one before we get to the main theorem. There's one. Right, and I left too big a. Oh no, I left a big enough space. Okay, so so I think most of the stuff here is pretty straightforward. Famous last words. But let me. But here's some consequences of the fact that of the characterization of Galois extensions. That Galois extensions are the same thing as splitting fields. So suppose K is a Galois extension of F, and G is the Galois group of K over F, and suppose some little g in big F, not necessarily reducible, splits completely in K with roots beta 1 through beta r. So maybe. Yeah, that's right. I guess so. This is it's actually important here. We actually use later that G might not be irreducible. I mean, so I guess right. So G might not be irreducible. G might not be irreducible. Okay, so and this actually it's this first bit here that's the most important part, or sort of the part that I want you to take away most strongly. So if K over F is Galois and L is an intermediate field between K and F, then it's true that K over L is also. So I should always draw this picture. So here K is the big field, and L is in the middle, and F is your base field. That's always a picture. Right. I guess it's useful to sort of draw a little diagram over here. So in green. So G, the full group G, is this group of automorphisms of. Yes, actually, it's very important to draw this picture. So that's the full group of automorphisms of K over F, and now you kind of you would think somehow maybe sort of naive is not the right word, but sort of intuitively you would think that somehow you'd actually want to study the stuff down here, right? You want to study you always want to sort of understand automorphisms over the base field. But that is actually not the thing that's most natural to look at here. Or that's not the easy part. So the thing that works well is actually automorphisms of K over L. And the idea behind that is that if you look at the automorphisms of K over L, those are by definition the automorphisms of K that fix L, and those fix L. So they also, we make the following silly observation: fix F, because F. So if you have an automorphism of K that fixes L, it must also fix the base field F, because F is contained in L. So just almost like as a tautology, just by the way we set things up, that means that the Galois group of K over L over the sort of the intermediate field, not the intermediate field over the base, is a subgroup of the full Galois group of K over the base field. And so one of the things that's really hard to wrap your mind around in Galois theory is that the natural thing to look at, not natural in terms of what a human being would think of, because I would never think of this first. I mean, if I had studied this, I mean, I probably wouldn't even think of it recently if I hadn't looked at it last night. So I mean, not natural in terms of like what comes into human intuition, but natural in the sense of like this is the way the universe is set up. The natural thing to look at is not when you look at something sort of sub-objects, you're not looking at the automorphisms of L over F, you're looking at the automorphisms of K over L. So nature is weird, but this is in some more literal sense the natural thing to do. Okay, anyway, so right, so subgroups, as we'll see in a minute, the subgroups of G correspond to automorphism groups of K, not of L over the base field. They're automorphisms not over the base field, but over the intermediate fields. So that's weird. That's like this. Once you get your mind around that, that's kind of the central weirdness of Galois theory. The rest is actually sort of pretty reasonable. Famous last words. Okay. Anyway, so right. So sorry. So that's the big one of this list of 4 other consequences. G. Okay. So big G. Will sort of fix the coefficients of little g, and so permutes the roots of little g on that set. All right, so if k is generated by over f by those roots beta 1 through beta r, then the operation on S is faithful. Right, faithful, which meaning, what does that mean? I'm almost certain that well, I know that in your shoes, even after having taken Galois theory once, for those of you who have taken it once, I think I would not remember what faithful meant. So let me remind you, or perhaps tell you, even if perhaps some of you haven't seen this before. So faithful means the kernel of the action of G on the set S is trivial. That is, any element of G that induces the trivial that fixes all these elements beta 1 through beta r is the identity. Well, that's true. So the kernel of the action of G on the set S is trivial. That happens because if you fix F and the betas, you fix K. Gee, actually, none of this, I see this, not really any of this really relies on as a consequence of Galois equal splitting. Oh, well, but it's the 4th one that does. Anyway, so right, why is the operation on S faithful? It's because if you fix, by definition, G fixes F, and if an element of G also fixes these things that generate K, well, then it fixes all K, because you got it, because everything is a consequence. Being fixed is a consequence of being having all this other stuff fixed. That means we can think of G as a subgroup of SR, the symmetric group on these R elements. And so whenever you can write K as being generated over the base field by a bunch of elements, then you can think of the Galois group G of K over F as a permutation group on those elements, and we'll use that later. And finally, here's the last part. So if G is irreducible, then G acts transitively on S that actually follows from this lemma up here, and the proof of this theorem. So in that case, this is from the proof of the characterization theorem, the proof of the theorem above, and the lemma used to prove it. That lemma, let me go back and show you that, just show you that lemma one more time. Well, this says exactly that there exists some element of the Galois group that sends the first root to all the other roots, and so that so that's what we get there. So, and let me note, we will later see/use a case where G is not irreducible, is actually reducible, not irreducible, and so and G acts non-transitively on S. Okay, so right. So any questions about that so far? About those four consequences? Well, and really consequences, not so much of, maybe not so much of that theorem, but consequences of the setup that we had in that section of 16.6. Are we ready to move on? Okay, I can do my old question dance. This is obviously dangerous, having this camera up here. Like my impulse to mug for the camera is irresistible. Okay, all right, let's go zoom back in and let's do it. Let us rock the main theorem of Galois theory. Yeah, okay. So let's do that. Main theorem. Oh, there it is, the main theorem of Galois theory. Okay, the main theorem of Galois theory says let K over F be a Galois extension, or that, in other words, let, as we were just saying, that let K be a splitting field of some polynomial with coefficients in big F, and let G be the Galois group of that extension. Then we have a bijective correspondence between the subgroups of G. Oh, right, I could not find this. Well, you know, there's this one character I had trouble finding, and right, correspondence between the subgroups of capital G and the intermediate fields of the extension. And not only do we have that bijective correspondence, here's exactly the description of the maps that of one particular bijection. On the one hand, one way in the Galois one direction the Galois correspondence sends H to its fixed field K to the H, and the other direction sends intermediate field L. Oh, that didn't quite work, but to see, I had the hardest time finding this character, which is supposed to be maps to, backward maps to, maps from, which is sort of useful when we're sort of going you know, to sort of retain this dividing line between things on one side of the world and the other. Oh, that was a mistake, but okay, well, never mind. You know, that's a good thing about lecturing online as opposed to in person, that I have this undo button. You know, if there's only an undo button in life, right? Anyway, so sorry. So yeah, the correspondence in one direction goes from. I wonder if this will like look correct, be in the correct direction. I guess we'll see when I watch the video for this. Goes from the one direction from subgroups to intermediate fields, and the other direction goes from a subgroup to its fixed field, and the correspondence the other direction goes from an intermediate field to the Galois group of the big field over the intermediate group. Not and remember, it's not not the first thing you would think of. It's not the Galois group of the intermediate field over the base field. It's the intermediate field of the top over the intermediate field. Now I'm really curious. So when I do those things like left or right and top and bottom, I guess top and bottom should did the left or right like work in the correct direction? Does it match what you see on the slide? I'm not really curious. Does it work? Yes, no? All right, actually, am I pointing towards the left of the screen right now? And what you see? Yes. Oh, no, now, okay, so now I have to do everything backwards. Oh, that's funny. So I'm pointing to your right now? So, oh, no, okay. So, oh, now I know what it's like to be an aerobics teacher. Okay, here we go. So let me try that again. So the Galois correspondence starts from sub. So if you start on the subgroup side, which is I guess is going to be your left, then you start with the subgroup is mapped to its a corresponding fixed field, and if you start on with the intermediate fields, going from fields to subgroups, you start with an intermediate field, and you go to the Galois group of K of the big field the sort of the full extension over L, and remember not the Galois group of the intermediate field over the base, which has a much more complicated relationship as we'll see, a more complicated relationship to G than the Galois group of the big field over the middle field. Did those lefts and rights match that time? Okay, so there we go. Right after this is all over, I'll be able to go into a second career teaching Zumba. Yeah. Okay. There we go. Well, or something like that. Anyway, so let's. So how do you prove that you have a bijection? Well, you prove so. So remember, just sort of start in a sort of fundamental level. So maps are bijective if and only if they have they're invertible. So it's enough to show that the two maps are inverses of each other. Okay, this capital letter is going to bother me. All right. So it's enough to show that the two maps are inverses of each other. So let's start with a subgroup H, which is a subgroup of G, of the Galois group G. So if we start with H as oops, I don't want to do that. With a subgroup H of G, then the Galois, the fixed field theorem. I mean, I guess the thing is, at this point, everything has been aimed towards setting this up, and so we're going to make this look like relatively straightforward, just because, well, we spent the entire course not the entire course, but at least certainly the last few chapters are completely aimed toward proving this one theorem. So it'll look like relatively straightforward. It's just that we did all the work already. So the fixed field theorem says that that H equals the Galois group of K over its fixed field. All right, so that direction was it's not so much straightforward. Oops, as it is, we did the work already. So great. So if we start with an intermediate field L, let's see. So So if we start off with an intermediate field L, here's where we're actually going to use the characterization of characterization. So sorry, let me put it this way. So if we start with an intermediate field L, the characterization of Galois extensions and its corollaries. Oh, there was actually one. Imply that K over L is Galois. And so L is equal to the fixed field of G of K over L. And so, well, so we're done. But okay, so let me point out exactly where that happens. So yeah, so once we know that K over L is Galois, this says exactly that the fixed field of that Galois extension is the base field that you start off with. There's nothing unexpected going on there, and so that's what we need. So, gee, I guess it is actually. We did actually make it look straightforward. All right, yay, we did it. Yay. Okay, so that's the proof of the fundamental theory, the main theorem of Galois theory. Fantastic. And the rest is somehow just all corollaries. Wow, okay. Neat. Oh yeah, but the picture is the thing I really want to draw here. Wow. Very clever person, Galois. I mean, okay, I don't want to put forth like this is somehow my idea. Is Galois is a very clever person. But are there any questions that we really did prove it here? Are there any questions about this so far? Robbie asks, what did the second line prove? You mean the one that says start with H is start with H or start with L? Oh, so start with A. So yeah. So what you want to do is you want to show. Let's call this. I'm going to try to show off my new left-right abilities. So let's call this over here. This is the left to right map, and this is the right to left map. No, that's a terrible. I'm just trying to. Okay, that's counterproductive. Let's say this is the fields to subgroups map, and this is the subgroups to fields map. Okay. So this line that says start with H says that if we first do subgroups to fields and then do fields to subgroups, you end up with the identity. So let me write that out. So this here says that this proves. Proves this first half set proves that subgroups to field, applying subgroup to fields first and then fields to subgroups is the identity. Right? You want to show that each of these maps, the subgroup to fields map and the fields to subgroups map, you want to show that each of those maps is invertible. And then in particular that these are inverses of each other, and the way you do that is you prove that doing the subgroups to fields map. Oops, there we go. Where are we here? doing the subgroups to fields map. Here's the which is sends H to K to its fixed field, and then doing the fields to subgroup maps, fields to subgroups map, sending K to the H to G of K over K to the H gets you back to H, and that's what we proved. And over here, the second thing, the third line shows that if we start with an intermediate field L, and we apply the fields to subgroups map, that takes L to G of K over L. And then if we then apply the subgroups to fields map, then we take the fixed field, we get back to L. And so, Robbie, does that make sense? All right, and thank you for forcing me to explain that as opposed to just saying "Yay!" declaring victory and going home. Okay, so quick pause. Where everybody else is good so far? Before I draw a picture. Okay, let's zoom back in, and I will now draw a picture of the Galois correspondence. All right, so let's see if I can sort of. All right, so the idea is, yes. So that's Robert says. So the structure of the subgroup lattice is tied to the field lattice structure. That's exactly. Thank you for pointing out. That's exactly what I'm about to draw. So let me start to draw that. So the idea is that right. I guess maybe in some ways it's more natural. Oh, there we go. It's more natural to think about what happens in the fields first. Well, actually, I'll just sort of start drawing. I will foolishly stick with what I had before and have fields on the right and subgroups on the left. Remember that the thing you want to keep in mind is that the big field corresponds to the smaller subgroup, and so what is the fixed field of F by the fixed field theorem? What is the group that has fixed field F? Well, by the fixed field theorem, it's exactly all the group of all the full Galois group G of K over F. So the first thing, one thing to note is that the full group, the big group capital G, corresponds exactly to the smallest field capital F. And conversely, what is the group of automorphisms of K that fix all of K? Well, there's only one automorphism of K that can fix all of K, and that's the identity. And so the trivial subgroup of G is what happens up there. So the trivial subgroup of G is exactly what corresponds to the full extension at capital K. Slightly better K here. All right, so I think it certainly helps at least to anchor sort of the top and the bottom of this diagram by remembering, well, you have the full extension K and the base field F, and when you look at essentially the stabilizers, not essentially, but when you look at the stabilizers of those particular subfields of K, well, the only stuff that stabilizes all of capital F is the stuff that stabilizes all of capital F is everything, the full Galois group G, and the only things that stabilize K, the only things that fix K are the identity subgroup. So now, sort of more generally, if we have an intermediate field L, and I think the classic way to draw this picture is that you have to imagine that there's other intermediate fields here in some perhaps some slightly complicated fashion. So that corresponds to, remember, some subgroup H, which is the Galois group of K over L, And remember, yeah, that's always sort of the for me, at least for me, the most confusing part of this is that you're always looking at the natural way to do this is you're always looking at the Galois group of the top part of the diagram, not of the bottom part of the diagram. Like I said, we'll talk about the bottom part of the diagram momentarily. And so okay, so they're all sort of more corresponding subgroups in there. Let's see, I guess. Actually, let me move this over a little bit. Right. So you want to think about L here is the fixed field of H. There we go. There's the picture of the Galois correspondence. Om, Om, Galois, Om. Anyway, so yeah, absorb it, love it, tattoo that on the inside of your eyelids. This is great stuff. So that picture makes some sense? And it occurs to me I should add one decoration to this. This is sort of like, this is always the danger of gilding the lily. So I'm going to take this and I'm going to make one decoration to this, which is I'm going to point out that this is an inclusion. No, that's not what I want. I want to do it the other way. So this is an inclusion reversing correspondence. So yeah, why did I draw the arrows that way? I'll explain in a minute. So the reason I drew the arrows, well, let me explain. So if we have two sets A and B, and we have that B, this is a slightly silly mnemonic device for why I drew that way. So when I draw an arrow from B to A, that means that A is a subset of B. I guess the arrow is supposed to represent this kind of like a mutated subset kind of deal. Yeah, so once I do that, you can sort of see like, well, the trivial subgroup is a subset of every subgroup H, and H every subgroup H is a subset of the full group G, and the subsets go the other way over here. So Om. Okay, yeah, Om. So there's the full picture of the Galois correspondence. I hope let me pull back here. Hopefully I've illustrated the inclusion reversingness of the whole thing. There. Yes. So good. I don't know if I've made the video any more visually interesting, but I'm amusing myself, which all you teachers know is the important thing. And so I think I'll keep doing this video inset deal. Okay. All right. So So that this is the picture. I think this when I remember learning this. At some point, I learned this pretty well. I think in grad school, and I remember this picture or some analog of this picture is sort of what I found to be really helpful. Oh, look, here's an example. Okay, so let's do an example. Yeah, I think we'll do an example, and then I think either we'll probably at least start a discussion of we still haven't we still haven't dealt with L over F, and so we'll at least start a discussion of L over F, and then maybe finish it on Wednesday. All right, so the biquadratic. So I think I pointlessly changed the numbers from the example in the book, but basically, if you have any two distinct non-square integers, then if you let alpha be root 5 and beta be, and this sort of, there's nothing special at 5 and 11. I think it's 3 and 5 in the book. If alpha is root 5 and beta is root 11, then alpha beta is root 55, and then and so let our base field be the rationals, and let K be the extension of F our base field, the rationals, by alpha and beta, and so f of x is let f of x be the non irreducible, the reducible polynomial x squared minus 5 times x squared minus 11, and I hope you all see, but I think I should probably type out here that K is a splitting field of F over F, of little f over big F. So now little f is not irreducible, so this is not necessarily transitive, and as we shall see, it is not transitive. Now, the degree of K over F, well, is because beta is not contained in alpha. That means beta has degree 2 over F of alpha. I guess this is worth sort of mentioning, as at least it's sort of degree of F of alpha beta over F of alpha. Here's one proof of this, times the degree of F of alpha over F. And we know that this is true. This is 2 because for example, x squared minus 5 is irreducible by Eisenstein, and similarly we can show that beta is not contained in F of alpha, and so this degree has to be 2, and so this is 4. Well, okay, so and then the question is, what is the Galois group of K over F? And did I leave it? Yeah. What is the Galois group of K over F? Okay, so let me start naming some elements of G. Well, there's sigma, and so let me say that they are permutations. So elements of the Galois group G can be represented faithfully. I mean, basically, they are permutations of the set alpha minus alpha and beta minus beta. The 4 roots of, those are the roots of F, of little f, sorry. Let me note that. Those are the roots of little f down here. We saw before that the Galois group is a permutation group on the roots of the sort of polynomial that used to make the splitting field. And so elements of the Galois group are just permutations of those things. So one of those permutations switches alpha and minus alpha. So this is a little, I know this is maybe a little bit of a weird notation, but I think it makes sense. This is cycle notation, so it's sort of like the 1, 2, like cycle 1, 2, 4, 3 or something like that. But instead of permuting the numbers 1, 2, 4, and 3, is permuting the objects alpha minus alpha and beta minus beta. So you have sigma equals, which which switches alpha and minus alpha, and leaves the betas alone. There you have the element tau that switches beta and minus beta, and leaves out the alpha, leaves alpha and minus alpha alone, and then you have sigma tau, which is equal to tau sigma, because these things commute, and that is the permutation that has 2 disjoint cycles, alpha minus alpha and beta minus beta. So those are and the identity. So So the extension has degree 4. This is, and we found 4 elements. So we're done. So that, in other words, G, the Galois group, the full Galois group G, it contains exactly the identity, sigma, tau, and sigma tau. Okay, so we have now computed the Galois group of K over F. Any questions so far? Okay, groovy. And so, now there's a question. Why, so Ravi asks, so why is G equal to a permutation group of alpha minus alpha, beta minus beta? That's what you're asking? Okay, so so that is a result. We said the result, but when you say a result, it looks really different than when you so that's exactly items 2 and 3 up here. So let's see. So suppose G splits completely in K with those roots. So first of all, we saw that G acts on the set of roots of that polynomial with coefficients in the base field. And then, in fact, if K is generated by those coefficients in the base field, if K is generated by the base field and those roots, then the operation on S is faithful. In other words, you can think of G as a set of as a permutation group, as a group of permutations on those roots. So it's a wee bit weird, just a wee bit weird here, that the natural way of thinking about a Galois group is not as a permutation group of like 1, 2, 3, 4. It's one very natural way of thinking about a Galois group is as a permutation group of the roots of that sort of the polynomial that you use to construct a splitting field. So so that is exactly those results 2 and 3, those sort of offhand corollaries 2 and 3 that we mentioned before. So that's why we think of G as the permutations of alpha minus alpha, beta minus beta. So that makes sense? Okay, 5 minutes. Let me actually draw the diagram that goes with this. So now I want to go, yeah. So I now want to draw the Galois correspondence over here. This sort of picture that works, general picture that works in the abstract. And now I want to draw that same picture over here in the particular. So I want to draw subgroups. So here is something where we know the subgroups of G pretty well, I think. They're all cyclic, or maybe after some review, you might remember that. So if we have, there's a trivial subgroup, and we have, and down here we have the full Galois group, which is C2 cross C2, the product of 2 cyclics. And each of there are 3 subgroups, each of which proper subgroups of G, each of which is cyclic. There's the cyclic subgroup generated by sigma, cyclic subgroup generated by tau, and the cyclic subgroup generated by a weird letter that I made by mushing together sigma and tau. Let's see if we can move sigma over a little bit. Sigma times tau. There we go. All right, so there's the subgroup lattice. Well, I guess the upside down compared to how this usually drawn. There's the upside. There's the subgroup lattice of G, and let's see. So over here on your right, which means my left, over here, I'm now going to draw. It's dangerous doing left and right here, huh? So I'm now going to draw the K, which is F adjoin alpha beta. That's the big, and then we have F down here. And so there should now be corresponding to these three. The main theorem of Galois theory says that these three subgroups of G must somehow correspond to the intermediate fields between the full extension K and the base and the base field F. And so, well, I guess so. Remember, I guess for me, I mean, I think I said last week that I said a little warning that now when I teach algebra, this is sort of teaching my native language, and now when we do group theory, I'm now lapsing into my native dialect of my native language, and so I tend to. I apologize. I hope I'm not doing this too fast. I tend to do things on this side a little faster than I do over here, just because like, well, I'm used to this. And I'm going to slip in my New England accent any moment now. Yeah. Anyway, so sorry. So we send each subgroup to its fixed field. So sigma permutes alpha and minus alpha. So over here, so the things that are fixed by well, beta is one thing that's fixed by swapping alpha and minus alpha. That leaves beta alone, and f of beta we know has degree 2 over f. And so that must be the thing corresponding to the cyclic subgroup generated by sigma. And so yeah, so I guess I'm going to go from left to right here. Yeah, so for each of these subgroups, I'm going to try to figure out what its fixed field is. Because at least for me, it's easier to figure out the subgroups and harder to figure out the fixed fields. And I think that's actually true in general, maybe pretty generally true, because that's why Galois also invented group theory. It wasn't called that at the time; they were only permutation groups, but still. All right, so tau. Remember, so tau is the flips beta and minus beta, and so the thing left alone by that group is alpha, and so the fixed field of the cyclic subgroup generated by tau must be f of alpha. And well, there's only sort of one suspect left here, but you might it's f of alpha beta. So where does that come from? Well, I guess I think yeah, that is maybe the sort of least immediate conclusion here. And so let me say why that's true. Sigma tau. Oh yeah, never mind. I should not do that. So the point is that sigma tau flips alpha goes to minus alpha, and beta goes at the same time goes to minus beta, and so alpha times beta goes to minus alpha times minus beta, which is alpha beta. And so so sigma tau actually fixes the element alpha beta, because they both that automorphism negates both alpha and beta, and so it leaves their product alone. Yeah. All right. So like I said, I mean, like I guess, oops, I did not want to say that. Do that. Look at those teeny tiny pages. So like I always say, and this is especially true at this part of this course, the general theory is cool. It's like, wow, that works great. And it's just when you get into the examples are really hard. So yeah, this is sort of like the sort of most the first interesting example where you get something that where you get something new out of the theory. And so anyway, and so that's why for the next 3 weeks we're just going to be doing examples pretty much. Anyway, so thank you very much for your time and your patience. And you could have been anywhere on the internet, but you chose to be here, or at least you logged in. So let me stop sharing and stop the video. Stop recording.